All right, so good evening once again. Good evening. So, we want to look at the deflection in an electric field, right? So don't forget that all of the things we have said, like I said, if you have questions, you can send them. Deflection in an electric field. Deflection in electric field. So in the previous video, I've stated that you have three series. There were three series I explained from the Baba series, where I said that you're going to be using 1 over lambda is equal to right back constant 1 n1 square minus n2 squares. Please don't forget, all right? I said also that for Baba series, it ends in n is equal to 2, Lyman ends in 1, all right? Lyman's ends in n is equal to 1. And I said that Pascal ends in n is equal to 3. So I did an analogy on that for the shortest, the series line, and the longest wavelength in the previous video. Alright, so do take note of this, and if there is a question you come across that you're finding difficult to solve, alright, so do well to reach out to us via my WhatsApp so that it can be attended to. Alright, so when you're talking about deflection, right, I've said in the previous video that deflection, right, is actually the change in the speed, alright, of light, change in the speed of any of electron or light when it passes from one medium to another. So when you're talking about deflection in electric field, so if an electron, because in atomic structure we are dealing with electron, but in photons the other is light. So this one is electron. So if an electron is entering into an electric field, what's going to happen? I said in that video, alright, the first video, that if your magnetic force is balanced with the electric force, there's not going to be deflection. Like none of that concept where we balance, that is from J.J. Thomson experiment, balance electric force with magnetic force. But if there's a deflection in electric field, it suggests that there's no balance force, alright? Because I said that if it's not equal to, it means that it's not balanced, alright, there's going to be deflection, but if it's equal to, there's not going to be deflection. So here, it is not equal to, so there's, now we are considering when there is deflection in the electric field. So if there is deflection in the electric field, what is going to happen? Alright, now let us look at first of all what a field is. Alright, a field is actually a region of space, okay, in which a force is experienced or is being experienced. A region of space where a force is experienced is called a field. Now when you talk about electric field, alright, there are different kinds of field. We have gravitational field, we have electric field, we have magnetic field, alright, and other etc. So when you are talking about electric field is actually a region or space where electric effect is felt. Alright, where electric effect is what is felt. So that is that. So there's a diagram we are going to be using for beam, alright, of an electron entering into a beam, alright, into an electric field. So use a beam for that experiment. So now if the electron enters, what's going to happen? Now we find our first acceleration for the electron. F is equal to ma, alright, force is equal to mass times acceleration. So what's going to be the acceleration for an electron that is deflected in an electric field, in case you are asked? Meanwhile, the path traveled by the electron is going to be parabolic in nature. Take note of that. I really don't want to go into the diagram. The path traveled by the, but you can check the diagram online, right? It's parabolic in nature. So what is your force? Your force is equal to ma, and your force from electric charge, according to J.J. Thomson's experiment, is EQ. I used E is equal to F by Q as an example. Electric field intensity is equal to force per unit charge, and your force is equal to electric field intensity multiplied by the charge. Alright, if F is equal to EQ, so anywhere I see F now, I can write, once this like electric force, I can write EQ is equal to MA. So what is my E? My E is equal to volt over distance apart. So I have volt over distance apart, Q is equal to MA. So my Q is equal to E. So I have V over D, then into E is equal to what? MA. So we have done all of those two before. But here in the concept, now just use our Q to be E and find acceleration directly in order to make our EV over D. So I have EE is equal to MA. Alright, so what is my A? So if my E is equal to MA, that's also that MA is equal to what? EE. So I have EE is equal to MA. Once I'm looking for A, I divide both sides by the mass of the electron, because the electron is moving, so it has particular mass of the electron. So this one has gone. What is left? I have what? EE over what? MA. is equal to A. So now A is equal to, so this electric field multiplied by the electronic charge over the what mass of electron. This is what we call the what acceleration. All right, that's what we use to calculate for acceleration. E here is electric field intensity in Newton per coulomb. E here, small letter E here is called the electronic charge, 1.6 times 10 raised to power minus 19 joules. Then M is the mass of electron. Mass of electron, for somebody that mistaken it, is 9.1 times 10 raised to power minus 31. Not 31. So this what's going to be the acceleration. Alright, when an electron is deflected in what? In an electric field. So don't forget this acceleration, this mass of electron, this electric field, electronic charge, mass of electron, and this acceleration. Acceleration, electric field, electronic charge, and the mass of electron. So mass of electron is 9.1 times 10 raised to minus 31 kilogram. Then your electronic charge is 1.6 times 10 raised to minus 19 joules. Okay, so that is what we have. Right, is your electric field intensity. If it's given the question, find it. Then what is going to be F? Now, if this is the value, now you are going to also calculate for this acceleration. All right, F is equal to ma. So if F is equal to ma, definitely, all right, m will cancel m. So you can now use F is equal to ee to calculate for the force. So electric intensity multiplied by the electronic charge will give you the value of the force. So let us find the horizontal distance. The horizontal distance now in motion, we know that if an object is moving from rest, our initial velocity is equal to 0. So my distance is supposed to be ut plus 1 over 2 at squared. Now the horizontal distance that happens when an electron is, all right, of course there are two distances there. There is the vertical distance and there is the horizontal distance. The vertical distance is actually this, all right, while the horizontal distance is x is equal to vt. All right, the horizontal distance, vertical distance of the electron is what is this, while the horizontal distance is x is equal to the velocity multiplied by time taken. So I will show all of that and how it works. So if you have to calculate for the vertical distance, once my s is equal to ut plus 1 over 2, right here, s is equal to ut plus 1 over 2 at squared. So my s is equal to y. The value of s here is y. So I have y is equal to ut plus 1 over 2 at squared. So if this value of y, which is the vertical distance, now what is my u? If the electron is moving from rest, my u is equal to 0. Then I have y is equal to 0 multiplied by t plus 1 over 2 at squared. So I have y is equal to 0 times t is 0 plus 1 over 2 at squared. So I have y is equal to 1 over 2 what? At squared. Alright, if my vertical distance of the electron is 1 over 2 at squared, then what is going to be the value of A? We said A already to what? E over me. So we can now say where, alright, A is equal to electric field intensity, acceleration is equal to electric field intensity, electronic charge over mass of electron is equal to this. So you recall this. Your y is equal to 1 over 2 at squared. So you now have y is equal to 1 over 2. Your A is now E over me, then everything into what? Into t squared. Okay, that's what you have as what value of the vertical distance. To calculate for horizontal distance, use this horizontal distance and the horizontal when an electron is traveling, alright, or is moving, is deflected in an electric field, and this is the what horizontal distance of the what? Of the electron. Alright, so if that is gotten, your y is equal to 1 over 2, this electric field intensity, this electronic charge, this mass of electron, this electric charge, and that's the time taken, alright, then all into square. This one is for horizontal distance, then this for vertical distance. So note all of those things as I put this acceleration, this force, horizontal distance, and this vertical distance of the electron. So now if that is gotten, alright, now the next thing you also want to consider is what we call the component velocity v prime of the electron. Alright, v prime, the component velocity. Okay, so what is the component velocity of the electron? Then there is also what we call the angle at the beam, because I said by using the beam, alright, there's angle, alright, with the beam emerges from the field, and there's the component velocity. So I'll show all of those two things basically, alright, then we'll move. Now for the component velocity, alright, but there's something I want to outline in that place before we talk about even the component velocity. But component velocity is given to be the value of acceleration multiplied by time. Alright, component velocity is equal to, it's just like from A is equal to V over T. Alright, then if A is equal to V over T, of course this A over 1 is equal to V over T. Alright, so you must multiply, so you have AT is equal to V, or V is equal to AT. But your V here is V prime. V is equal to V prime, alright, which is now V prime is equal to what? AT. And